Hello, hello, everyone. Hope you're all doing well. Hold on, let me just center my camera. Make sure it's pointed at me. Make sure it's focused. All right, here we are. Today I thought we would have some fun and go over the 10 easiest problems ever to appear on the Putnam exam. If you don't know what the Putnam exam is, it's an exam for college math students. It's an extremely difficult test. Hello, Ken. How are you? Let's see here. It's an extremely difficult test. Oh, hello, Mohammed. Hope you're well. And I hope you can all hear me as well. I'm just going to draw the little border around my head. Okay, so if you don't know what the Putnam exam is, it's an extremely challenging test. Basically, it's 6 problems, and you have 6 hours to do it. And I believe the median score for this test is a 0. So most people don't get any problems at all taking this exam. So don't be surprised if these problems are challenging and if you don't get even one of these. But it's of course fun if you do get one of these. So I just thought we'd have a look at the 10 easiest ones. By the way, these are the 10 easiest ones in my opinion. You may have a different opinion about what the 10 easiest problems are. And I thought we could go in chronological order. So I'll start. So these are in no particular order. They're not ranked like hardest to easiest or anything like that. I thought we would start out with the earliest year and go to the latest year. I will say that I do believe these tests have been getting harder and harder as the years have gone by. So you would expect the problems appearing in past years to be easier than the more modern problems. And with that in mind, let's get started. So the first problem here, and yeah, we're just going to rifle through these just to have a good time. So you have a right circular cone, right? You have a right circular cone, which has a base radius of 1 and a height of 3. So you have a right circular cone, which has a base radius of 1 and a height of 3. And inside this cone, there is an inscribed cube, so that, the bottom face of the cube sits at the very bottom here. So you can imagine there's a cube sitting inside here, so that the very bottom face of the cube touches the bottom face of the cone. Okay. So the question is, what is the side length of the cube? What is the side length of the cube? The thumbnail looked pretty bad. Yeah, it's actually not as bad as it looks. So just so you know, there's always one problem on these Putnam exams, which is slightly easier than the rest. Okay, I believe it's so that you can potentially bank time to do the later problems, which are significantly harder. But in any case, this is the first problem I have for you. You have a right circular cone. It has a base radius of 1 and a height of 3, and there's a cube inscribed inside it, so that the bottom face of the cube touches shares a face with the bottom of the cone. And the question is, what is the side length of the cube? That is the first question here. Okay. Yeah, so right circular cone means this angle is 90 degrees. So it stands upright. So the vertex of the cone is directly above the center of the circle at the very bottom. Okay. So and just so you know, in my opinion, I do believe that this is the easiest problem that has ever appeared on a Putnam exam. So that's just my opinion. I'm by no means like a scholar or anything. Yes, the 4 upper corners are touching the cone as well. Absolutely. So I'm by no means a scholar. I just spent yesterday going through Putnam problems, and this I think is the easiest one that I encountered. By no means saying it's easy, but this is the easiest one that I happen to encounter. Okay, so I guess I'm gonna give away the solution now. So cover your ears if you don't want to hear it, or just say something in the chat. Tell me to pause if you want me to stop at any point. Okay. So just to repeat the question, you have a cone. It has a base radius of 1. It has a height of 3. And then there's a cube that sits inside the cone. It's inscribed inside, so all its corners are touching. So how would you find the side length of the cube? Okay. So, all right. I'm going to give this away because, like I said, I do want to keep going. But here's what you do. Slice the cone like right where the diagonal of the cube is. So what I want you to do is imagine taking a knife to this cone and cutting it like exactly where the diagonal of this cube is. Notice if you do that, you'll get a triangle. Like if you look at the slice of the cone that you get. Yeah, you're exactly right, Ken. You look at the diagonal, okay? Now, if the height of the cube is s, let's say, right, then, okay, so I guess that's the start. So the height of the cube is s, and this is s. This is going to be s root 2, because the length of the diagonal of a cube is going to be s root 2. Well, I'll try to do that with the next problem, Mohammed. I'm sorry. I feel like I've mostly given this one away, so this is s, and just keep in mind this bottom length is 2, and the height of this triangle is 3. And so now at this point you just need to solve for s, which is not too challenging. So for example, so I can pause here for a moment and give you guys a second to finish up solving this problem. Okay. Maybe some of you have already figured it out, but essentially this triangle and the big triangle are similar triangles. Like this triangle and like this, these are two similar right triangles. And the ratio of the base to the height in these two right triangles is 1:3. So immediately you get that like this bottom section over here, I'll color it in white. Whatever s is, this section here is going to be s over 3. This little bit over here, right? So essentially, and this is because this is 1:3 and this is 1:3. Okay. Also, what you get is this section here, like this piece over here, is going to be s root 2 over 2, right? Because s root 2 is the top, so this is going to be s root 2 over 2. So if you add s over 3 to s root 2 over 2, you should get 1, okay? So you add s over 3 to s root 2 over 2, you should get 1, and that allows you to essentially solve for s. So now the denominator is 6. This is 2s plus s times 3 root 2 is equal to 1. So s is in fact 6 over 2 plus 3 root 2. You can rationalize the denominator, of course, if you so choose to. So if you did that, you would have to multiply the denominator by the numerator and the denominator by 2 minus 3 root 2. And so if you did that, this would be so 2. Let's do it the other way. So this would be 18 minus 4, which is 14, and this is 6 times 3 root 2 minus 2. And so you get just, and so the 2's cancel. And so the final answer, if you choose to rationalize the denominator, is going to be 6 root 2, 9 root 2 minus 6 over 7 is going to be the answer for S. So this particular problem was asked in 1998. This is the first problem on the 1998 Putnam exam. The way you cut the cone is you cut it so that your knife slices the cube on its upper diagonal. So if you imagine this is the cube, right, sitting inside the cone, you would want to have your knife go through the very tip of the cone and also cut the cube right here, like right on that edge. Let me know if that makes sense. That is precisely where you cut the cone. Okay. So this is, there it is. So the answer is 9 root 2 minus 6 over 7. And like I said, I do believe, in my opinion personally, I do believe this is the easiest problem to have ever appeared on a Putnam exam. I did try to go through them all, but I may have missed something. So there you have it. So let me know if there are any questions about that, and I will move on to the next one. So, okay, let's move on to the next one. So the next problem is, given 5 points on a sphere, you need to show that 4 lie on a closed hemisphere. Okay, so you have 5 points on a sphere. So you have a sphere, and you have 5 points on the sphere. And you want to show that 4 are on a closed hemisphere. Okay, so there are 5 points on a sphere, and you want to show that 4 lie on a closed hemisphere. If you're unfamiliar with this idea of closed hemisphere means just including the equator of the hemisphere. Okay, so you have 5 points on the sphere, and imagine slicing it so it slices into 2 equal pieces. Closed hemisphere just means you are including the equator. So one of those 4 points could lie directly on the equator of the slice you make when you slice the sphere in half. Let me know if there are any comments on this question. And yes, closed means you are including the bounding circle. That's exactly right. That's exactly right. So 5 points on a sphere, you want to show that 4 lie on a closed hemisphere. So let me know if there are any questions about this. And so this particular question appeared in 2002 on the Putnam exam. This is the first problem on the 2002. So I believe this is, so there are 2 versions of the exam. There's an A version and a B version. This was the first, actually, I think it was the, let me double check. I have it in my notes over here. It was the second problem on the A version of the exam. So it's a 2002 A2. 5 points on a sphere. 4 points you want to show lie on a closed hemisphere. How might you do this? And I'll give you a hint. It's just a 1-line answer, truly. Well, maybe not 1 line, but it's a very short. There's a very quick answer here. And let me know if there are any questions. And in about 10, 20 seconds, I'm going to give away the answer, just so I can keep up the pace of the stream. Okay, here goes nothing. So if there are no further questions about this one, so there are 5 points on a sphere. You want to show that 4 are on a closed hemisphere. Here's how you do it. So there are 5 points somewhere on the sphere. What you want to do is take any 2 of them. Okay. it's because you can pick any 2 points to be on the equator. That's exactly right. So, on an equator, not there's no the equator, but you're exactly right. So if you have 2 points over here, you can pick what's called a great circle that goes through these 2 points. So on any 2 points on a sphere, you can pick a great circle that goes through those 2 points. Okay. Now, that leaves 3 points, right? So you have 2 points going through here, and that, of course, leaves 3 points. Now, you just have to think about how these 3 points are going to be divvied up. And, there has to be, one of the sides has to contain at least 2 points, right? This is by the pigeonhole principle, right? So one of the 2 sides has to contain 2 points, right? Because these 2 points are gone, they're on the equator, and there are 3 points to go. And, the split in the 2 hemispheres can be, 2-1, 3-0, 1-2, or 0-3. And in all of those cases, you see that there are 4 points on a hemisphere. Yeah. Okay. So that's my number 2 problem of my 10 easiest problems to appear on a Putnam exam. Of course, all these seem easy when you have the solution, but they're kind of hard to think of when you're there. So let me talk about the next one, which is this is the okay. Let me state the problem, and then I'll tell you the year that it goes on. So basically, you're keeping track of the number of successful free throws for a basketball player. Okay, you're keeping track of the number of successful free throws for a basketball player. So essentially, you're keeping track of a fraction, right? So the number of successes over the total number of attempts. Okay, so you're keeping track of the following ratio. You're keeping track of the number of, successful free throws divided by the number of total attempts. Okay, so you're keeping track of the following ratio, which is the number of successful free throws divided by the total number of attempts. At the start of the season, you have that this number is less than 80%. Okay, so at the start of the season, you have that this number is less than 80%. At the end of the season, it just so happens that this number is greater than 80%. And so the question is, did there ever have to be a moment when the percentage was equal to 80%? Okay? Was there ever a moment where the percentage have to be exactly 80%? Okay? So this is the question. Let me find the year for you while you guys figure it out. So this is 2004 A1. You're exactly right. If you had an hour, Ken, I think you could have gotten it. But remember, I feel like the easy ones you're supposed to get done really quickly because the last couple are super duper brutal. So if you're aiming for a high score, these first couple problems are designed to be just gimmies, I believe. But like I said, even so, the average person taking the test is not going to get even a single problem. But let me repeat the question. So over the course of a season, you're keeping track of the following statistic for a basketball player. You're taking the number of successful free throws divided by the number of total attempts. Okay? At the start of the season, this number is less than 80%. At the end of the season, the number is greater than 80%. Was there ever a point when the number was dead on 80%? Why or why not is the question. Let me know if there are any people freshly joining. If you'd, yeah, absolutely. If there are any people freshly joining, let me know if you want me to repeat the question. I'll say it one more time. So you're keeping track of, for a basketball player, the number of successful free throws divided by the number of total attempts. At the start of the season, this number is less than 80%. At the end of the season, the number is greater than 80%. Was there ever a point when this number was exactly equal to 80%? Why or why not? So Ken says his intuition says no. Any other guesses or ideas for this question? Same. So Muhammad also agrees with this. So, yeah, your intuition says no as well. It's a fair point. Unfortunately, it turns out both of your intuitions are unfortunately incorrect. Okay? This is, I believe, what makes this a trick question. I think most people would guess that it doesn't have to be exactly... For that exact reason, because integers need not divide cleanly. I think most people's intuitions would suggest that there's no point where it needs to equal exactly 80%. But it actually does. So let me give you the argument as to why that's the case. So let's try it out. So in this case, what you need to do is let's just think about it. So you're keeping track of this number, right? Let's say I'm going to write it as m over capital N, which is how the official solutions write it as well. So write this number as m over capital N. Okay. At the start of the season, this number is, of course, less than 4/5, which is what 80% is, right? So m over n at the start of the season is definitely less than 4/5, okay? But at some point, this person, let's say, hits a free throw, at which point the ratio goes over 4/5, right? Let's say that, let's say your intuitions are correct, okay? Then the following has to be the case. So at some point in the season, this number is less than 4/5, but then this person sunk that one free throw, at which point this number became greater than 4/5. Okay? So far, so good? So, 3/5 to 8/10 to 9 over 11 is a counterexample to the no answer. Well, unfortunately, you... Hold on. So you have to be careful with your logic, Tommaso. So basically, if someone says something is always true, all you need to do is provide a counterexample. Okay? If someone is asking if something is ever true, right, and you want to prove them wrong, you need to show that it can never work in any circumstance. Okay? So for example, if I say it rains every day in Florida, you just need to find me one day that it doesn't rain in order to prove me wrong. Okay? But if I say there is a day where it rains in Florida, you must show that it never rains in Florida in order to prove me wrong, right? So you just have to be a little bit careful about that. Okay, but anyways, let's continue with this. So, so you have this situation where m over n is less than 4/5, but m plus 1 over n plus 1 is greater than 4/5, right? But of course, what does this mean? This means that 5m over capital N is, let's do it like this. So basically from the first inequality, we have that, 5m is less than 4n, right? For capital N, right? But from the second inequality, you would get that 5m plus 1, right, is also going to be greater than 4n, right? So 4n is now an integer between 5m and 5m plus 1, which gives you a contradiction. Okay? So let me know if that makes sense. All right. Well, Seems like that made sense. I'm going to move on to the next question. Okay, so that was 2004 A1. Now we are going to, sorry about that. So that was 2004 A1. So now we're going to move on to 2004 B2. Okay, so this is 2004 question B2. Okay, here's what you need to show. So m and n are positive integers. Okay. What you need to show is that m plus n factorial divided by m plus n to the m plus n is less than m factorial n factorial divided by m to the m, n to the n. I will say this is a deceptively simple problem. Okay, but I want you guys to take a look at it and think about it. So, by the way, which one are we on? So we're on, this is 2004 B2, which I believe is number 4 out of 10 problems. So m and n are positive integers, and you want to show that m plus n factorial over m plus n to the m plus n is less than m factorial n factorial divided by m to the m, n to the n. Why would that be the case? So I'm telling you that this is true. This is not a number. Well, okay, I don't know. Maybe this is a number. but I swear there's it's not really number theory here that's making this one tick. In fact, I'm not sure how many number theory problems I even have on here. Let's see here. There's one, I guess, number theory kind of heavy problem, but just one. Well, only 1 out of the 10. I guess that reveals my bias. Maybe I find a number theory to be a bit difficult, but I swear this is at least one of the ways to solve this. There's a non-number theoretic approach to solve this problem. So this is 2004 problem B2. So m and n are positive integers, and what you want to show is that m plus n factorial over m plus n to the m plus n is less than m factorial n factorial over m to the m, n to the n. I understand, Tomato. Sorry, I missed your comment earlier. So, how might you do this? I'll give you guys a hint. Do you see any potentially familiar expressions in this one? Is there any way to rearrange this? Okay, I'm about to say it. So, if you do some manipulations to this, it'll become like this. It'll become m plus n factorial divided by m factorial n factorial. And I'll multiply that also by m to the m, n to the n. And you want to show that this is less than m plus n, m plus n. Okay? But notice this particular expression over here is actually m plus n choose m. M to the m times n to the n equals. I think maybe Ken, some of what you typed may have been erased by formatting issues, but I suspect you were onto the right thing. So here's what you have. So you have m plus n choose n times m to the n to the n is less than m plus n to the m plus n. Can you? Does this seem somewhat familiar? Any reason why this one might be true? So notice that these two are equivalent to each other. It's okay, Tomonsa. Don't worry about it. But are there? So these two are definitely equivalent to each other. So proving one is the same as proving the other. So the question is, why is the second one true? Any ideas? So I'll just say this. The second one is true because this is just one of the terms in the binomial expansion of this. So if you just expand the right-hand side using the binomial theorem, the left-hand side is guaranteed to be one of the terms in that expansion. Yeah, that's exactly right, Siwan. It is a binomial theorem. So the left-hand side is guaranteed to be one of the terms if you expand the right-hand side. That's correct, Duke. And so, you're good to go. That proves it. So because everything is positive, we are done. Okay? And so there you go. That is my, where are we at? So that's my number 5, I believe. In chronological order, easiest problems to have ever appeared on the Putnam exam. Once again, that does not make them easy. Just, in my opinion, happen to be just one of the easiest ones on this particular exam. All right, let's do another one. So this one is from 2005. And so you want to find a polynomial, pxy. So this is a polynomial in two variables. Maybe it looks like, xy minus x squared, y squared plus 3x, whatever. It's just a polynomial. Actually, I don't know why I wrote a homogeneous one. It could also include like x's and y's on their own. Something like this. So pxy is a polynomial in both x and y. Hopefully that doesn't scare anyone away. So pxy is a polynomial involving both x and y. Okay. Your goal is to find a polynomial. So find a non-zero polynomial pxy so that if I hand you a real number a, right? So if a is a real number, then when you do p of the floor of a, comma, the floor of 2 times a, you always get 0. Let me know if there's anyone out there who in the chat right now who doesn't know what a floor is. A floor is the smallest integer less than a number. So the floor of like 2.1 would be 2. Okay. Hopefully that all makes sense. So it's the integer just before a real number. And if you plug in an integer, it's just equal to the same thing. So, the floor of 2 is just 2. Okay. So you want to find a polynomial pxy, a non-zero one, so that if you plug in the floor of a and the floor of twice a, you always get 0. And just so you can look it up on your own, this is problem... it's problem B1 on the 2005 exam. Okay. So, no reason to be scared, Ken. Luckily, none of us are taking the test at this moment. So, yes, the floor of negative 2.5 is negative 3 indeed. That is accurate, Ken. I feel like the polynomial must be homogeneous. I don't know why would you say that? Also, I want to give you guys a big hint. Oh, that's a very interesting idea, Mohammed. But I'll remind you that we're flooring as well, right? We're taking floors. So that kind of messes up the whole like scaling idea. You see what I mean? I would start with 2x minus y and build from there. Duke, you got it. Good work. So here's the thing. You can check this and just try a couple examples if you don't believe me. But either the floor of 2a will be twice the floor of a, or it will be one less than that. Okay? So, for example, if you take 2.1, which is the number we've been using, right? The floor of 2.1 is 2, right? And then the floor of 4.2 is 4. So in this case, the floor of this real number 2.1, the floor of the double is the double of the floor, right? Let's see what happens if you do 2.6. So the floor of 2.6 is 2, right? And then the floor of 5.2 is 5. So 1 over, right? So, and these are basically the only two cases. So it's like a one-liner again, if you happen to see it. And so it's just x, so it'd be like 2x minus y, and then 2x minus y minus 1 is a polynomial that works. There it is. Good work. Good work, Duke Garland. Okay. Hopefully that makes sense. All right, let's move on to, I believe, number 6. So, also, let me know if there are any questions about that. The one in the thumbnail. So you want to find the volume of the following region. I'll give you guys a little bit longer for this one. So the region is defined by the following equation. So the equations are x squared plus y squared plus z squared plus 8 quantity squared is less than or equal to 36 x squared plus y squared. Okay, so this is the equation. What is the volume of the region inside R3 that's defined by the following equations? Oh, also, Duke, I just realized it should be y minus 2x, and then it's y minus 2x minus 1, not 2x minus y minus 1. But whatever, it's close enough. You'd get like 9 out of 10 points for your answer. But it's just the other way. So the double can be, the floor of the double can be 1 larger. So it's just the other way. But whatever. Moving on. So what's the volume of this region? So in this case, this is, by the way, 2006 problem A1 on the Putnam exam. So what is the volume of this region? And how would you figure it out? This one is the intersection between a sphere and a cone, I think. Are we allowed graphing? No, you are not allowed any kind of computational device, I don't think, on this exam. Okay, I'll give you a hint. This, it says 10 easiest problems on the Putnam exam is the title of this video. So you know there's some shenanigans going on here, right? Like there's no way there isn't something going on here with this equation. So see if you can't play with the equation a little bit and see if something happens. And I'll give you another hint. Maybe you want to use cylindrical coordinates. Just let me know how it goes. So We're finding the volume of this region. All right, so I'm about to give it away. Hope you guys have enjoyed thinking about it. So what I'm going to do first and foremost is think about this in cylindrical coordinates, and I'm going to take the square root of both sides after I do that. So I have here, r squared plus z squared plus 8 quantity squared, but I'm taking the square root of both sides. Well, let me just write it out, I guess. Less than or equal to 36 r squared, right? So if I take the square root of both sides, I have r squared plus z squared plus 8 is less than or equal to 6r. Okay. So, but notice if you, here, let me move this up a little bit. Move it up. Done. You can take the 6r on the other side. So now you have r squared minus 6r plus 8 plus z squared. Actually, hold on. You want to do less than or equal to 1. So I think I'm going to do a 7 here. Okay. So, oh wait, sorry. It would be a 9. Okay, math. They say you should never do math in front of a live audience, and so now you see why. So in any case, now I have this r squared minus 6r plus 9, but then this goes again, so this is r minus 3 quantity squared plus z squared is less than or equal to 1. Okay? If you stare at this for long enough, you'll realize that this is the equation of a torus. Actually, this is the equation of a donut. So you're taking a circle and then you're rotating. So you're taking a disk and you're rotating that disk about an axis. Okay. And remember, if you have a situation where you need to compute the volume of a, if you need to compute the volume of a solid object that's obtained by rotation, you have this thing called Pappus's theorem, right? I think you learned this in Calc BC, but so for those non-Americans here, Calculus BC is like the final calculus exam that students in America take. But there's a theorem. It just disconnected for a second, but give me a sec. Hello? Let me know if people are still there. I think OBS disconnected for a moment. Yeah, just say like hello or something if if people can hear me and are still there. Okay. Regardless, the way you compute the volume of a solid of revolution is you just take the area of the object that you're rotating. You also need to find its center of mass, which in the case of a disk is just the center of the circle. And you compute the distance of the center of mass to the axis about which you're doing the rotation. The product of those two numbers is going to be exactly. So the product of those two numbers is going to give you exactly what the volume is. Okay? So in this case, what is the area of the disk in question? The area of the disk in question is going to be pi because the radius of this disk is going to be 1, right? And we are, the distance through which the center of mass is being rotated is going to be 6 pi, right? And so the answer here is going to be 6 pi squared. Okay? Let me know if that makes sense. Sorry that one got weird. I sorry, like the stream dropped for a second. But you can check that this equation really is the equation of a torus, right? And then you are rotating a disk of radius 1 about an axis, and its distance to the axis is going to be 6 pi. So it's just 6 pi squared is going to be the volume here. Okay. Sorry, that one got a little messy because the stream dropped, but let's move on to the next one. Maybe we'll have a clearer time. And also let me know if you have any questions about this one at all. Ken says I would have gotten that one. Yeah, this one, especially if you've recently taken a calculus class. Well, I guess if you've recently taken a calculus class, that can be both a benefit and a hindrance, because if you've recently taken a calculus class, I feel like the temptation to break out an integral it would be very strong in this situation. But the key is to not do that, that you can just use something like Pappus's theorem, or realize that this is just a simple objective revolution type problem. Okay, let's do the next one. This is, I would say, the only like kind of number theory-esque one on this list that I have here. So let's say f is a polynomial with positive integer coefficients. Okay, so f is a polynomial with positive integer coefficients. Let me know if any of the words in the question are not clear. So f is a polynomial with positive integer coefficients. And we know that here. So f of n divides f of n plus 1 if and only if n equals 1. That is the question. Okay? So f is a polynomial with positive integer coefficients. And you want to show that if f of n divides f of n plus 1, then it must be the case that n is equal to 1. Okay? Why is this the case? So try to do either direction and see if you get it. So let me just find the year for this problem. This was 2007 B1. So this is 2007 on test B, problem 1. In case you want to look it up later. So f is a polynomial with positive integer coefficients. Then f of n divides f of n plus 1 if and only if n is equal to 1. Why is this the case? What is going on here? So just to keep in mind, there has to be some trickery, right? Otherwise it wouldn't be on this top 10 list. So let me know if there are any questions about this at all. Okay. And if there are no questions, I will start diving into the solution here. So f is a polynomial with positive integer coefficients. You want to show that f of n dividing f of n plus 1 is the same as n being 1. Okay? Why would this be the case? Well, let's think about this for a second. Okay. What we are going to do is we are going to work mod f of n. Okay? So f of n dividing f of n plus 1 is the same thing as saying that the remainder of f of n plus 1 is 0 when you divide it by f of n. One way to write that mathematically is f of n plus 1 is congruent to 0 mod f of n. This is just another way of saying the remainder when you divide this by this is 0. Okay? Hopefully that is clear. All right? Now, let's think about this. F is just some polynomial with integer coefficients, you know? So I'm going to say in the corner here, let's say like F is just this polynomial. It's, you know, let's say F of n is just, you know, am n to the m plus am minus 1 n to the m minus 1 plus all the way down to a0. Okay? So that is, so I'm just saying what the coefficients of f are. I'm declaring that I'm going to call the coefficients of f am through a0. All right? Hopefully nothing crazy has happened just yet. If these are the coefficients of f, you know, am through a0, then this becomes am fn plus 1 to the m plus am minus 1 fn plus 1 to the m minus 1 all the way down to a0. And we're saying that this is congruent to 0 mod f of n. Okay? But here's the thing. F of n is congruent to 0 mod f of n, right? So in other words, f of n is 0 mod f of n. So you can replace each of the f of n's here with 0 because their remainder when you divide by f of n is 0. Okay? So in other words, the remainder when you divide this big ugly mess by f of n is just going to be am times 1 to the m, right? Am minus 1 times 1 to the m minus 1 all the way down to a0. So here you just get am plus am minus 1 plus all the way down to a0 is congruent to 0 mod f of n. Okay? Let me know if there are any questions about this step. Granted, if you've never done modular arithmetic before, this might seem insane. It is possible to do this question without any modular arithmetic. All I'm saying is that you can replace each of these f of n's with 0 because the remainder when you divide f of n by f of n is 0. And that's a legal move to do in a modular arithmetic. So now you have am plus am minus 1 all the way down to a0 is 0 mod fn. But what is am plus am minus 1 plus a0? You'll notice that that is just, what about the exponent before dividing through? Here's the thing. If fn has a remainder of 0 mod fn, you can replace this fn with a 0. And so now you're just doing 0 plus 1 to the m. And 1 to the m is just 1. Okay? Does that make sense? All right. So notice, by the way, that am plus am minus 1 plus all the way through to a0 is just f of 1. The sum of the coefficients of the polynomial is the same thing you know, you get when you plug in 1 into a polynomial. Okay. So f of n plus 1 being congruent to 0 mod f of n is the same thing as saying f of 1 is congruent to 0 mod f of n. Okay? So let me rewrite what we've just proved without making reference to modular arithmetic. So f of n divides f of n plus 1 if and only if fn divides f of 1. In other words, f of n divides this number if and only if f of n divides this number. Right? But notice f of 1 is going to be less than f of n unless n is equal to 1. So the only way that f of n can divide f of 1 is if n is equal to 1. And that's it. So There you go. So as you notice, as the years go by, even the easiest problems on this test are getting harder. But yeah, I do think this one is reasonable. You just need to be relatively comfortable with modular arithmetic. And if you're not, I'm sorry, but don't worry, there are other problems coming up. So let me know if there are any questions about this. We will move on to the next one. So this is the one and only kind of like number theory. Like this is the only one on here that required anything like modular arithmetic. Okay, so let's do this next one. So let's say you have a regular icosahedron. Okay, so suppose you label the faces of a regular icosahedron with, why is f of n less than f of 1? I missed that. The only way f of n can be less than or equal to f of 1 is if f of n is equal to f of 1. Because remember, the coefficients of f were all positive whole numbers, right? So we expect the function to just keep getting larger if you plug in larger values. So the only way f of n can divide f of 1 is if n is in fact equal to 1. Hopefully that answers your question, Ken. Okay. So suppose you label the faces of a regular icosahedron. And also make sure all the labels are different. So all, actually, no. Sorry, it's like giving the answer away. So suppose you label the faces of a regular icosahedron, okay, with a non-negative integer, okay, with a non-negative integer. So 0 is allowed, okay? Okay. You label the faces of a regular icosahedron, each with a non-negative integer, in such a way so that the sum is 39, okay? You want to show that two faces that share a vertex have the same label. Okay. Two faces that share a vertex have the same label. Have the same label. All right. So you're labeling the faces of a regular icosahedron with a non-negative integer in such a way that all these non-negative integers add to 39. You want to show that two faces that share a vertex have the same label. All right, that is the question here. I'm just going to verify that I have the problem statement correct. So for those of you who want to look this one up, it's 2013 problem A1. Okay, so you're labeling the faces of a regular icosahedron with non-negative integers in such a way that they add to 39, and you want to show that two faces that share a vertex will have the same label. Like there are two faces out there that you can find that share a vertex and have the same label. Why would this be the case? By the way, if you don't know what an icosahedron is, let me just pull one up for you. So hopefully I can find a nice, here's an icosahedron for you, in case you don't know. An icosahedron has 20 sides and 12 vertices, okay? So these are just important facts that you need to know about icosahedra in order to solve the problem. So an icosahedron has 20 sides and 12 vertices. Let me just put this over here so you can look at it. Not really sure where to put it, but hopefully you can see that. Maybe make this window even smaller still. Put this maybe up. Okay. hopefully this is reasonable. So, this shape, it has 20 faces and it has 12 vertices. There's the icosahedron. Notice that every vertex neighbors 5 faces, okay? And of course, every face has 3 vertices. So now you want to show that 2 faces that share a vertex, like 2 faces that are touching each other via at least one vertex, will have to have the same label. Why would this be the case? So once again, you're labeling the faces of a regular icosahedron with non-negative integers, so 0 is allowed, in such a way that the sum is 39, okay? And you want to show that 2 faces that share a vertex will have to have the same label. Why might this be the case? A hint. Look at the 5 faces that label a single, that neighbor a single vertex. So, okay, so think about the 5 faces that neighbor a single vertex. What would what's the smallest possible sum of the labelings of those faces, assuming it's all distinct? It's all distinct, okay? So if what I'm saying is wrong, it should be possible to label this thing so that if you look at any vertex and all the faces neighboring that vertex, they all have different labels, right? So what would be the minimum sum of the labels of all of the faces that neighbor a vertex? So I hope that was an interesting hint. Ten is the min for vertex. That's absolutely right. Pankaj, you're correct. You want to use some principle. So 10 is the minimum for every vertex. Okay. Let's say you add that number for every vertex. What would happen? What do you get? No, 0 is allowed, Mohammed. So you're adding 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So IHTFY is correct. It's 10, and Ken, you're correct as well. Okay. So let's think about this sum that we've just constructed. Okay. So I have my icosahedron, and around every vertex there are sort of 5 neighboring. This is terrible drawing. Try again. That's better. Okay. Around every vertex, there are 5 neighboring faces. And what I'm going to do is I'm going to add up the weights on each of these faces, right? If I do this, I'm going to get, if it is true, right, that all of these are different for every vertex, I have to be getting numbers for each of these that are at least 10, right? If I do this for every single vertex, right, if I do this for every single vertex, remember there are 12 vertices, so I'm adding the weights of all adjacent faces, right? I'll get 120 total. So I get 120 total, and, by the way, if you're alarmed by the size of this number, it's reasonable because a lot of the faces are being counted twice, right? So for example, if you do the same for this vertex, then these two faces will be counted a second time. But I've just constructed this sum where for every vertex, I look at the 5 adjacent faces and then I add up all of their weights. And I know that that number has to be at least 10 if I'm using distinct numbers around every vertex. And so if I compute this sum for every vertex on the entire icosahedron, I have to get 120 total. Agreed? Okay. Now I want you to think about in this sum. So by the way, how did I get this sum? So add up the weights of adjacent faces for all vertices. Okay, so I add up the weights of the adjacent faces for all vertices, and that gives me 120 total. And notice, as Ken has already pointed out, every face is counted 3 times in this, right? Every face is going to be counted 3 times in this. Every weight is going to be counted 3 times because every vertex so every face is adjacent to, every face contains 3 vertices. So you can divide this by 3. So here's the thing. So this sum counts each weight thrice. How do I know this? Because every face has exactly 3 vertices. Okay, so this sum is going to count each weight thrice. And so that means that the sum total of all the faces in this sum has to be at least 40. But remember, it was a condition of the problem that the sum of all the weights was 39. And so we have our contradiction. Okay, let me know if there are any questions about that. All right, so this was 2013 A1. So hopefully it seems reasonable. Okay, I believe we only have one more. And do let me know if there are any questions about this one. Okay, so we have one more problem. So here it is. So this is from 2016. So we're going to construct the following sequence. So x0 is 1. Okay, so that's how it starts. And then for n greater than 0, you do the following. You define xn plus 1 to equal the natural log of e to the xn minus xn. Okay, so it's a recursively defined sequence. So x0 is 1. So for example, x1 will be the natural log of e minus 1, right? X2 would be the, natural log of e minus 1 minus the natural log of e minus 1, and so on. You just keep going. And so the question is, what's the sum of this series? By the way, it converges. You have to show that too. Though I might skip some steps there. So what is this in this situation? What is the sum of the series here? So x0, x1, x2, x3, all the way going on forever. What is the sum of this series? Also, in case you want to look this up, this is 2016 B1. So what is going to be the sum of this series. Pankaj, excellent instincts there. Can you show how to make it work? Maybe do something like yeah. A lot of you are are picking up on the trick here. Yeah, it is telescopic. Man, you guys, I'm very impressed. Good work. So this is it. This is indeed going to be telescoping. I'm running out of time, so I'm not going to show that it does converge. So first of all, what is the limit of this sequence? You can solve for the limit of this sequence by just setting x equals the natural log of e to the x minus x, right? And immediately you can figure out that. Wait, what am I doing? Well, okay, I'm like tripping over myself. But you can figure out that the limit of this sequence is going to be 0 without too much work. And from there, you can do a little bit more work and show that the sequence does converge. But figuring out what it converges to is the tricky part. And so to do that, you just take e, raise both sides to e. And now all of a sudden you have e to the xn plus 1 equals e to the xn minus xn. And so xn is equal to, let's see here, e to the xn minus e to the xn plus 1, right? So you can get from there, using a telescoping argument, that the series is going to converge to e minus 1. So if that doesn't make sense, let's see here. You can, here, let me say it like this, just in case people are not clear. So what we managed to figure out is that xn is equal to e to the xn minus e to the xn plus 1, right? And so if you add x0 all the way to xn, for example, you're going to get e to the x0 minus e to the x1, but then plus e to the x1 minus e to the x2, and so on, all the way to e to the xn minus e to the xn plus 1, right? And so significant cancellation happens. This is the telescoping argument people were alluding to in chat. E to the x0 is just e, and by just looking at the limit of the sequence, you can figure out this xn plus 1 part is going to 0. And so e minus 1 is going to be the limit of this. I shouldn't say equal to, I should say the limit as n goes to infinity. Okay. A little sloppy at the end there, but I hope that all made sense. So this was my top 10 picks for the easiest problems to have ever appeared on a Putnam exam. I hope you all enjoyed that. Let me know if there are any questions, but I'm probably going to head out now. Thank you all so much for showing up. I really, really appreciate it. And I'll be streaming again on Saturday at 1 p.m. Eastern. I think I'll be deriving E equals MC squared then, unless you guys have a better idea. Let me know if you guys want me to do something else. But if not, I'll be deriving E equals MC squared. So I think that'll make for a fun stream. I wanted to save it for Saturday because more people show up on Saturday, and I thought, whatever, they might enjoy it. All right. Again, thank you so much, and peace.